Can anyone confirm if audio and video everything is fine before we get started? And like people in the chat, like how many problems were you guys able to solve today? So like that will give me some idea on like which problems to focus more and which problem probably we can pass on as an easy problem. So by the way, like I have written a Codeforces blog with hints for problem ABCD, and I am planning to discuss ABCDE1 today. And like I don't know how to solve problem E2. So like that would pretty much be the agenda for today. N square time complexity, like N square time complexity, I think may be fine for C, but definitely like the number of queries you ask should be less than 15. So like that is the slight difference. Like so like any tips, like you can probably check my Discord server, like there is a channel roadmap to read in 2 minutes. You can probably check there to see what advice I have for the people. And I think I will probably start from A only, obviously. And like let's get started now. No, not problem A, problem A only would be the first one. Problem A says you are given a cyclic array A1 to N. You can perform the following operation on A at most n minus 1 times. Let M be the current size of A. You can choose two adjacent element where previous one is greater, number is greater than the latter one. In particular, AM and AI are adjacent and AM is the previous one. Delete exactly one of them. In other words, choose an index I where AI is less than equal to this holds and delete exactly one of these two values from it. Your goal is to find the minimum number of operations needed to make all the elements equal to AM. So like probably let's look at some of the examples here. I will probably like to discuss one of the samples. Any feedback, like give me an array of 6 elements, 7 elements. For example, let's take this 1, 2, 3, 2, 1, 4, 1. Let's say 2. And let's say like we want final element to be 2 here. And let's also like let's ignore this condition for now. You like choose an index where this should hold. Like let's just ignore this condition. Let's say like AI less than equal to AI plus 1 is allowed and AI greater than equal to AI plus 1 is also allowed. Then like what would be the answer over for this array? Any comments? Let's say here if you want final element to be equal to 2, then you know for sure that all the elements not equal to 2 must definitely be deleted from the array, right? Because we are only deleting elements from the array, we are never changing them. So like this must be deleted, this must be deleted, this must be deleted, this must be deleted. These elements must be deleted, and it can happen that we may have to delete some of these 2's here as well. So the answer will always be greater than equal to 4 in this case. Because if you want final element to be 2, all the elements not equal to 2 must definitely be deleted. And it can happen that we may have to delete some of the other 2's as well. Similarly, let's say if we want final element equal to 1. then all the elements not equal to 1 must be deleted, right? Because we are only deleting elements. And we may have to delete some of the ones as well. So the answer in that case would be greater than equal to 5. Any questions so far? So like why I am saying answer should be at least 4 if you want final element to be 2. How I am finding answer must be at least 5 if you want final element to be 1, and so on. Or in other words, what I can say is, if I want V to be the final element, and FV is the number of times we present, then like minimum, like to keep V, as final element, we must delete all other elements and some of the V's. This implies like answer to keep V must be greater than equal to n minus FV. And the critical observation here was, like, in case we did not have this condition, we could have just selected any element I which is not equal to the nearby or previous element, and we could have just kept on deleting the element here. But even with this condition, even with a condition like this, it holds that we would be able to delete all the other elements and we will never delete any V. So answer here for V should be n minus number of times V appears. And the way we can do over here is like, let's write some array. Let's say we want to keep final element as 2. Answer V basically means if we have to keep V as the final element, what should be the final element? Final element as 2. What we can do see is like we can try to choose indexes where we can delete any element greater than 2. If we choose I equal to 1 now, then I1 less than equal to I2 does not hold. So let's keep 3 for now. Keep further. See, we can delete 1 and 2 here because A3 is greater than equal to A4. So delete this one. Now like remaining arrays here is 3, 2, 2, 4, 4. We can also delete this 4 because A3 is less than equal to A4 and we can delete any index 3 and 4. We would be left with 3, 2, 2, 4. Now choose third index again. A3 is greater than equal to A4. Again delete 4. Now the remaining array would be 3, 2, 2. And it turns out because the array is cyclic, and here it holds like, although like A1 not equal to A2, this does not hold. But A3 less than equal to A1 holds because it's a cyclic array. So after 3, next element is 4. And now we would be even be able to delete 3. And like this would be the idea we can keep going. Like So like we would always be able to delete all the elements which are not equal to V, which we want in the final. So what we know is like if we want V as the final element, number of operations required is n minus Fv, where Fv is the number of times V appears. And to find minimum answer, find maximum value of Fv. Like basically choose the element that appears maximum number of times. And like this was essentially my solution for this problem. The idea was like this condition is receiving, like if this does not, because we want all the elements in the final array to be equal, we can keep trying to delete elements. We can fix first final element and we can try to delete all the other occurrences. And if it holds, because the array is cyclic, we would always be able to compare it with the last element and get our work done. So I will probably share my solution for this problem as well. Let me fetch my keyboard. I can create an array of size +1 to keep count of all the elements that are present. And at last, n is equal to n minus f of I. Like if we want I as the final element, then like n minus number of times would be the remaining element. We should delete all of them, because if we want minimum, keep taking the minimum. Or like another way is to find the maximum value of fi and subtract that from the answer and get it. Okay, submission is not allowed. So yeah. Any questions on first problem before I move on to problem B? Any questions on the first problem before we move to problem B? The main idea was like find the element which appears maximum number of times, and n minus that maximum value is your answer. So like also like any tips, like once I'm done with discussing all the problems, I would be happy to answer chat questions, tips or anything you have. Like for now, like I will first focus on discussing the solutions because most people are for that purpose here. Okay, I will move to the next question. Okay, let's move to B. Like problem B is slightly non-trivial problem statement. So let's, instead of reading, like I will just read problem statement 1 and then I will try to explain with some ideas what's going on here. There is an integer sequence of length n where each element is initially -1. Mitsuki has two typewriters where the first one writes the letter from left to right with the pointer initially pointing to 1, and another writes letters from right to left with the pointer pointing to other. Mitsuki will choose one of the typewriter and use it to perform following operation until A becomes a permutation of 1 to n. Write number. Write the minimum positive integer that isn't present in the array to the element ai I be the index where the pointer at, such operations can be performed only when ai equal to 1. Carry is return the pointer to initial position, that is 1 for your first writer and 2 for your second writer. Move the pointer to the next position. Let I be the position pointer at the before this operation. If Misuki using the first writer, I becomes I plus 1. And otherwise I equal to I minus 1 would happen. Such operations can only be performed if I is between 1 to n. Your task is to construct any permutation P of length n such that the minimum number of carriage return needed to make A equal to P is saved no matter which typewriter Misuki is using. So let's probably first see what's going on over here before we try to find minimum maximum whatever the problem statement asks. Let's say like the final, give me a permutation of 6 elements, people in the chat. Okay, let's take this 3, 4, 2, 1, 5, 6. Let's say this is the final permutation we want to write using the typewriters. And like, let's see like how does the running operation can work over here. First, we will have an array where all the elements are -1. And let's use typewriter 1. Initially, the typewriter 1 would be here. And we want to write 1 somewhere because that is the smallest element not present here. So we don't have a choice. We cannot write 1 here because we want 3 here. So we move to the next index. We cannot write 1 here because we want 4 here. We move to the next index. We cannot write 1 here because we want 2 here. So we move to the next index. Now like we can write 1 here because that's the final element we want. So far we are moving further. Now what we can do is like we can probably see that for 2 we will have to come back. And the only way to come back over here would be to go back in the starting again for the typewriter 1. Now the idea would be again, we want to write 2, we cannot write here, so we move further. We want to write 2, but we want 4 here, so we move further. When we are here, we want 2 and the smallest element not present in this array is 2 here. So we write 2 here, and because we want 3 here, for 3 we will have to come back. So there is no way we can just keep going and writing over there. At some point we will have to go back to the starting array again. Now the smallest element not present is 3 and we are here. And because we can write 3 here, we will just go ahead and write 3 here. And now we move further. The smallest element not present is 4 and here also the element is 4. So we will write 4 here. We move further. We cannot write anything because this is not -1. We cannot write anything because this is not -1. We move further. We want the smallest element not present here is 5 and we want to write 5 here. So we will write 5 here. And then we will move a bit more further. The smallest element not present is 6 and we want 6 here. So we will write 6 here. And you can see like right now, like 2 times we went from some index to back to the first index. Like these type of operations are 2 here, once here and once here. And you can probably see that 2 would be the minimum number of times you would have to come back to starting to write this permutation using typewriter 1. So the answer in this case would be like for typewriter 1, number of times we have to go to starting would be 2. Similarly, use the second typewriter which starts from n. Let's say we have 6 minus 1. The second type of typewriter is at this index. We want to write 1 first, and because 1 is not present anywhere, and we want 6 here, cannot write anything. So we move a bit further. Here also 5 is present, but the smallest element not present in this array is 1. So if we write anything, 1 would come there and we can't do anything. So we move a bit further. Now we are here. The smallest element not present in the array is 1, and we want to write 1 here as well. So what we can do is we can just write 1 here, and then we can move further. The smallest element not present here is 2, and we want to write 2 at this element. So we can write 2 here. Then we can move further. The smallest element not present here is 3, and we want 4 here. So we won't do anything here, we move a bit further. And the smallest element not present is 3, and we want here the element present to be 3. So we would write 3 here. Now we don't have a choice, like we can't go any more further. So we will go back to the starting position again. Now the second time, you can probably see we want 4 as the not present element not present here. We will keep moving further. We will reach here. Smallest element not present is 4, and we want element over here to be 4. So we will write 4 here, and then we will have to go back to the starting again. Now we are here again. We want 5 to be written, which is not present. We want 6 here. So we will move a bit further. We see like 5 is the element we want here. So we will write 5. And then we will go back to starting again. And in starting, like the smallest element not present here is 6 right now. So we will write 6 here. So you can see like probably the minimum number of times we have used to write this array using the second type of typewriter. When we have to go back to n back is 3 times. And you can probably see like this greedy algorithm is correct. Like 3 is the minimum time we will need to write using typewriter n. And 2 is the minimum time when we will have to go back to starting when we use typewriter 1. And the problem here is, like any questions first, like how the typewriter is working over here and what type of operations we can do over here. And the problem here is like, you can probably by now realize by this algorithm I have found the minimum number of operations. For typewriter n minimum times we have to go back to n index is 3, and for other typewriter it's 2. And because 3 is not equal to 2, so like the number of, so this is not a valid permutation we need. Because the problem says construct any permutation p of length n such that minimum number of carriage written, basically for typewriter 1 going to 1, for typewriter 2 going back to n. Operations needed to make a equal to p is same no matter which typewriter we are using. So like this is how the statement is working. So like this is not a valid answer we have. Or in general, let's find index of all the elements. Or probably let's just use our again favorite permutation 3, 4, 2, 1, 5, 6. And let's write down all the indexes where all the elements appear. IDX 1 is present at index 4. One is present at index 4. 2 is present at index 3. 3 is present at index 1. 4 is present at index 2, 5 is present at index 5, 6 is present at index 6. And now probably let's look at any of these two elements. For example, this. Here like 3 appears before 4. So when you are starting from permutation 1, like the typewriter which starts from 1, you will go somewhere write 3 and then you can continue going further to write 4 as well. While if you start at index n, when you write 3 somewhere, you will have to go back to starting and then come back again to write 4 somewhere. So basically if 3 appears before 4, then we have permutation which starts from 1. We would not need to go back to starting to write 3 to 4. But we will have to go back to the ending when we want to write 3 after 4. Or similarly, let's look at this case. When we start from the first element, we will go there somewhere write 2. Then we will have to go back to starting and then come at an index where we can write 3. While if it is second type of permutation, we can go directly to write 2 first and then we can use the same loop to write 3 as well. So now you can see like for any pair I and I plus 1, one of the permutation will have to go back to starting, one of the typewriter. Must go to starting and another other one will continue going further. This is the case when you want to find the minimum number of operations. Now can you see like why this holds before I proceed further? Impossible, possible cases, etc. Yes, so you can see like from 1 to n, we have n minus 1 such pairs. And if S1 is the minimum number of operation for first typewriter and S2 is the minimum number of operation for second typewriter, then their sum must be equal to n minus 1, because for every I and I plus 1, one of them will go to starting and another one will not go to starting. So if we want S1 equal to S2, we need to have S1 equal to S1 by equal to n minus 1 by 2. And like this is the reason why when n is even, it's impossible to have S1 equal to S2, because these are integers and even minus 1 is odd by 2 is not an integer. So we should directly print minus 1 if n is even, and if n is odd, we want to find a permutation such that S1 equal to number of return times we return to starting for both the permutation is equal to n minus 1 by 2. Now there are many different constructions possible over here. My idea was I will write 1 in the starting, 2 at the end. So when I write 3 here, for the first type of permutation, 1 will go to 2 and then we'll have to come back to starting. While for the second type of permutation, when we write 1, we will have to come back to starting and then we would be able to write 3. So if we have some elements like this 1, 3, 2, then to write elements from 1 to 3, both the permutations will have to go back to starting one time. Then the next idea was write 4 here and 5 here. So when someone has written 3, first type of permutation can go to 4, but it will have to come back to starting to write back 5. While for the second type of permutation, after writing 3, it will go back to ending, then 4 and 5 would be the way. So this is how I was writing elements over here. This is one way to write. So this is one of the valid answers. And I think different people had different ideas. I think someone in the chat told that this is the permutation they wrote. Something like that. Probably we can verify if it holds. 1, 2, 3, 4 will be written in starting. 5, go back to starting. 6, go back to starting. 7, go back to starting. 8, go back to starting. So this works. And if we are going from here, 1, go back to starting. 2, go back to starting. 3, go back to starting. 4, go back to starting. Then 5, 6, 7, 8, 9. Yeah. So like these are two valid ways to write an answer. You can either go write a permutation like this, or you can write some numbers like this and then some numbers in descending. So for the first type of permutation, you would write 1, 2, 4, 5 in one go. Then you will have to go back to starting to write every other number. And for the second type of typewriter, you will have to go back to starting initially, and then 5, 6, 7, 8, 9 you would be able to write in a sequence. So this can be one another way to solve this problem. Any questions on problem B before we move to problem C? Why -1 for even? Sure, I can repeat that again. So one thing I proved is like, if we look at index of two consecutive elements, for example 3 and 4, if 3 is at index 1 and 4 is at index 2, so for the first type of permutation we will start from here, we will write 3 and we will continue going to write 4. But for the second type of permutation, we will start from somewhere, we will first write 3, then we will have to go back to starting and then come back to write 4. So you see, if like index of 3 is less than 4, second type of permutation will need one extra go back to starting operation. Similarly, if we look at 2 and 1, where 2 appears after 3, in that case, first type of permutation will write 2 somewhere, then it will have to go back to starting and then write 3 somewhere. While the other type of typewriter, it can start from here, write 2, write 3 and continue doing here. So you can see, like for every pair of adjacent element, one of the permutation based on which one appears before the other when looking at their direction. For one of the permutation, you can continue going further to write that element, and for the other permutation, you will have to go back to starting. So from 1 to 9, 1 to n, there would be n-1 such consecutive pairs. And for each consecutive pair, one of the permutation will have to go back to starting and other will not go back to starting. So if S1 is the minimum number of operations for the first permutation, S2 is the minimum number of operations for the second permutation, then their sum must be equal to the number of adjacent pairs we have, which is n-1. And if we want S1 equal to S2, then both of them must be equal to n-1 by 2. And you can see if n is even here, like for example 8, 8 minus 1 is 7, 7 by 2 is 3.5. And that is why the answer is impossible for even. And how the checker might be implemented for B, like we can use the same logics here. We can find the index for each of the element. We can look at these two adjacent elements and we can either increase S1 for 2, because 2 appears before 3, we will increase S1. And because similarly for 3 appears before 4, we will increase S2, and we can keep going that. So like basically the way to implement checker is for each element find at which index it is present, and for every consecutive pair look at which one appears before the other, and based on that increase S1 or S2, and at last check both of them are equal or not. And you would have to also check if a person has printed all the permutation here instead of 1 1 1 1, not, something like that should not be present, and all the elements should be between 1 2, and so some basic tests like this. And this was my idea for problem B. Any questions? Any questions on problem B before we move to problem C? Okay, moving on to C. Okay, the problem statement says there is a hidden tree. Let's just create some tree there. And what you can do is, like, for each query you can select any two elements, any two nodes, let's say 4 and 5. If you ask query for 4 and 5, it will give you a minimum index, minimum node, give a node x such that distance of x comma 4 minus distance of x comma 5 would be minimum possible, and in case of tie it will give the index where distance of x comma 4 is minimum. Like, basically, if there are multiple elements with this as a minimum value, then it will give the element which is near to 4. And the critical idea over here was this element is nothing but the midpoint of part from the 4. Midpoint of path between A and B. How do I came up with this observation? Let's say this is A. There are some nodes here. This is B. There are some nodes like this. Let's write the distance of, let's write distance from A using a white pen. This is a distance 0. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's also write distance from B in a blue pen. Minus 0, 0, 1, 1, 2, 3, 4, 5, 5, 6, 7, 7, 8, 8. And you can see, like, this is a path where distance from B is 6 and A is 0. If we keep increasing here, the distance remains same. While if we go here, the distance from B decreases. Looks like I messed up somewhere. This is also 3, 4, 5, 5, 6. And looks like I wrote wrong values even for blue. Let's create a tree first. I think this diagram is now correct. Okay, read the problem statement first. Okay, probably, sorry, forgot about that. It says this is an interactive problem. Mitsuki has chosen a secret tree with n nodes, index from 1 to n, and asks you to guess it by using queries of following type. Query question mark AB. Mitsuki will tell you which node x minimizes the distance of A to x minus distance of B to x, and we have to take absolute value. Where dx comma y is distance between node x and y. If more than one such node exists, Mitsuki will tell you the one which minimizes the node from A. Find out the structure of Mitsuki's secret tree using at most 15 into n queries. Okay, so like let's say this is how the tree looks like. This is the path from A to B. Using white, I am writing the distance from A. Using blue, I am writing the distance from B. And looks like I am still messing up somewhere. 0, 1, 1, 2, 1, 2, 3, 3, 4, 5, 5, 6, 6. And for y 0, 1, 2, 0, 1, 2, 0, 1, 2, 3, 3, 4, 5, 5, 6. Yeah. So like distance elements written in white are distance from A, elements written in blue are distance from C. If you look at any part here, the distance from B would always pass through A, and this will always be equal to distance between A and 4. So the difference here is 4. Similarly, if you look at any node here, shortest path from A to any node here would pass through B, and the difference here is 4. While if you look at these nodes here, the difference here is 4. But if you go a bit right, distance from A increases and B decreases, and the difference becomes 2. If you go a bit further, the distance from both of them is same here. So the difference here becomes 0. Similarly, if you go further on this path, now the distance from A increases, B decreases, and absolute value is still 2. And here the absolute value would be 4. And if you go here, like the difference, like the distance or any node over here would be like the difference to reach here and here, because any path which goes from here will have same number of nodes here as well, 0. And you can see like there are two nodes where the minimum value 0 appears, and the solution says in case multiple values are there, it will give you the one which is nearest to A, which in this case is 0. So, and you see like this is essentially the midpoint of path from A to B. And you can probably try out even for the other type of distance as well. And if you write down the differences here, like I am ignoring all the nodes because by now you realize going outside the path will have same distance as going from one of the node in the path. Difference here is 5, it becomes 3 here, it becomes 1 here, it remains 1 here, it becomes 3 here, it becomes 5 here. Here again the answer we would get here would be this. This is the midpoint of the node, just that there are two midpoints, so it gives us the midpoint which is near to A. So any question on how like this query is giving you the midpoint of path from A to B? Any questions on this first before we try to solve it a bit further? Yeah, like significance 15 into n will come. Like the significance of 15 is log 1000 with base 2 is around 10. So 15 is just high number. It essentially says you should find the answer in log 2n queries. This is what my solution would be, and like I believe the intended solution was also in the lines of like this. So like 15 is approximately equal to log n, which is 10, gives you a factor of 1.5 to try out something. And essentially, like, why would it be closer to L? Because the problem statement says if more than one such node have same value of this, the answer will give you the one which is near to A. Now, like the significance, I will say the solution first, and then we can probably come back to 15 and part again. The significance is pretty much like you can not just try out all the ways there. So my idea is I will root tree at 1 and I will find parent of all the nodes. And if we know the parent of all the nodes tree rooted at 1, then we would obviously know all the edges because parent to child are the only edges in the tree. So my idea is like this is my root. And let's say I want to find parent of u here, say this node. What I can do is I can first query from 1 to u. It will give me the midpoint, let's say somewhere here. Let's say mid 1 is the midpoint this. Next what I will do is like now I will query for midpoint of mid 1 and u. Like basically now query for midpoint of this path. It will give me this node. Let's say this node is mid 2. Now I will query for like basically you choose one as a root and you choose other node. When you want to find parent, you keep finding the midpoint of these nodes. So first I found this as the midpoint. Now I ignored one and I looked at the midpoint of this and this. This green was the midpoint. Now I will query for midpoint of 2 comma u. This will give me this node. Let's call it mid 3. Now query for mid 3 comma u. Because mid 3 is the parent of this. This path has only one node. So like both of them would be the midpoint and nearest to mid 3 would be this. So this will again give me mid 3. And I can break over here and I can say like whenever I have got would be mid 3 here. So basically my idea was like first I realized this operation gives me the midpoint of path from A to B in the secret tree. And in case there are more than one midpoint, it gives me the midpoint which is closer to A here. So what I can probably do is, yes, I am assuming 1 as the root. So what I am doing is I first assume node 1 as a root. And for every other node, I try to find the parent of that node. The way I do is like I first look at the path from 1 to u. I try to find the midpoint. Whatever node I have got, instead of 1 now I look at this small path here, trying to find the parent again. So I look at the midpoint on this path. This time this would be the midpoint. So I discard this, I look at this path. On this path I would get this as the midpoint. Now I have just parent of u and u. And when you query on the path from parent of u to u, like because the path length is 1, both of them are at equal distance, and because it gives us the node closer to pu, so if we get pu back, we can know for sure that pu would be the idea. Like basically the idea is query from 1 to u, whatever answer you have got, now query with that answer to u. Now some other answer you will get, now use that answer and query for u, for that node and u. If you keep doing it, there will be a time when you will keep getting the same answer again. And when you are getting same here, no, how are you choosing u? I am not choosing u. I will iterate from u equal to 2 to n, because I want to find parent of all the nodes. So like u, my for loop will run from u equal to 2 to n, so that I know parents of all the nodes from u to n, and 1 is the root, so there is no parent here. And essentially like this is the idea. No, like at least I don't see screen flickering. Like, is it the case with other people in the chat or just for Neymar? Okay, video is bad. So this was at least my idea for problem C. I can probably write the code for it. Okay, background camera probably not sure. Yeah, like background camera probably when fan runs, the green screen doesn't work. Yes, Arya, in your case also like the queries would be log n only. Just look at a chain with 1 to 2 to 1 to n, and like essentially the solution you are sharing is what I coded in the contest. But it might be possible to have worst case time complexity of n log n there. So yeah, like essentially what you are saying is what I coded in the contest, but yeah. So I have this method which queries for node from 1 to n. So I am using one base indexing. Probably we don't need one base indexing. For u equal to 2 to n, one is definitely the ancestor for it. Let's query for midpoint of ancestor and u. If this midpoint is equal to ancestor, we know that pu is whatever the midpoint we have right now. So we can say edges dot pushback mid comma u and then break. Otherwise we say that a near another ancestor we have found is mid here. And like this would be the code for this, and at last print all the edges we have found. So like this would be short and sweet code for this problem. Okay, like the system testing is still not over. So I will probably submit all the code I have for ABCD so far over there. And this was the idea. Probably I think I forgot to say the code for B. Code for B was pretty much either you can reverse some part or you can use a two-pointer kind of approach and code it. So this code should work for B. Like you can try out different optimizations, but I believe like whatever you do will take n log n operations there. You can have some constant factor to reduce some number of queries there, but in the end, whatever you got would be some constant multiplied by n log n. That constant can be half, 2, 3, 1/3, anything there. And you can see like because we are, if n is the length of path, okay, now the significance of 15, and let's get back to it. So the first time you query, whatever you get is like the new path is almost the half of the length. Second time you query, the distance between those two nodes becomes half again. So you see like initially if the distance is between two nodes is 1000, after first query distance between two nodes would be 500, then 250, so on. And if you keep going it, at last the distance would be 1, and in that case when you keep doing half, nothing will happen. So like you see like we would approximately need log n number of operations to get a parent here. So overall number of queries we need, like because for each parent we need around log n operations. Total queries is n log n, somewhere like that. So like in our code, like log n is around 10. So we need around 10 into n queries. And significance is 15n is saying find something approximately equal to n log n. You can probably have some extra queries for something extra there. How do we know distance of a comma b is the value of middle node? Distance of minimum is not the middle node. It says two things. It finds the node which has this value as minimum, and in case multiple values exist, it gives us the value which has the minimum distance from A as well. And these two constraints together forces us to say that X would be the midpoint, which would be near to A on this path. And the way we find it, like by taking a working example, here I have drawn like white node denotes distance from A, blue nodes denote distance from B, and orange denotes the absolute value of difference over here. So you see like here the difference would be 4. Here also the difference is 4, and when we are looking at this path, here the difference is 4. When we go further, distance from A increases but difference from B decreases. So 4 to 2 becomes 2, 0 becomes, and then we go past the midpoint, this distance keeps on increasing. And for any node we go outside, the distance remains constant. So for example, here 0, if you go here also the distance becomes 0, and so on. So like there can be multiple nodes which are attached to midpoint but not on path from A to B can have same value of difference. The second constraint which says that in case multiple exists, it will give you the one which has smallest distance from A as well. And that is what forces us to say that this will always be the midpoint here. Okay, laptop I am using is probably Dell Inspiron, probably 14 or 15 inch, something like that. It's around 4 years old now, no longer in warranty or anything. So any questions on this problem statement before we move further to problem D? So the idea is like when we have a node like this A to B, just this path, distance from A would be 0 here, 1 here. Let's probably draw this graph. 2, 3, 2, 3, 1, 2, 1, 2. From distance from 3 is 0, 1, 2, 1, 2, 1, 2, 2, 3, 3. You can see like the difference is always 1 for all the nodes. And it says whenever you have equal distance, it gives us the node which has minimum value from minimum distance from A. And like minimum distance from A to A is this node. So that's why when A and B are connected by an edge, you query for A and B, you will always get an A. So I am not querying anything. I'm just looking at like this is node 1. There would be some node U in the tree. First time you will get some midpoint. Now query on this path, you will get a new midpoint. Now query on this path, you will get some new midpoint. At last, there would be a time when there would be one U, there would be one parent U, and now if you keep querying, you will always keep getting PU back. And that would be the time when we know that the node would be U. Yeah, for query we should pass nodes, so that's what I am doing. I start with one endpoint as 2, another endpoint as 1. Whatever midpoint I have got, if it was same as my previous midpoint, I say this is the parent. Otherwise, I move back to parent and new, parent and new, parent and new. Like I no longer look at the distance here. For query, like this is a function which prints the node and gives us the minimum distance. The solution gives us the node, not the distance between the nodes. Or you can even do something more smartly here. If you even don't want to check like this, you can just run a for loop. Keep assigning whatever midpoint you have got as a parent. And at last, when you are done with running this loop 15 times, whatever value you have finally would be the parent here. You can in fact do this as well. You keep querying midpoint, keep querying midpoint, keep querying midpoint. And like this would be the idea. You can even do this. You can say parent, new parent. If new parent is equal to parent, break. Keep doing this. Like query is returning the node which gives us the minimum value of this, which is what is said in the statement. You give A to B, it will give you a node X, which node X satisfies some of the conditions there. So it kind of is giving us the middle node instead of minimized distance. So any questions on problem C before we move on to problem D? I think I did not simplify B, so probably I can skip this something. So any questions until problem C before we move on to problem D? Not sure where in my submissions went, but yeah. So yeah, here we are. I will wait for a minute or more and then I will move to problem B. Okay, the next problem says longest Max Min subsequence. You are given an integer sequence a1 to an. Let S be the set of all possible non-empty subsequences of A without duplicate elements. Your goal is to find the longest sequence in S. If there are multiple of them, find the one that minimizes lexicographical order after multiplying terms at odd positions by 1. So for example, if A is 3231, all the possible element which does not contain duplicate would be 1, 2, 3, 2, 1, 2, 3, 3, 1, 3, 2, 2, 3, 1, 3, 2, 1. And the one which contains maximum number of elements would be 2, 3, 1 and 3, 2, 1. Because these two contain 3, 3 element, all the other elements contain 1 or 2 element. And then it says the maximum answer here would be 3 to 1. Because when you multiply odd indexes by minus 1, your array becomes in this case is minus 3 to 1 and minus 2, 3, 1 if you multiply this. And if you compare them lexicographically, this is smaller. A sequence C is a subsequence of D if C can be obtained from D by deleting serial, possibly 0 or all elements. A sequence C is lexicographically smaller than sequence D if and only if this condition holds. So, first question I have in the chat, like, what is the maximum number of elements we can have in the set S? Or what is the length of longest sequence we have? Or probably people in the chat, can you give me an array of length 10 which contains element from 1 to 4? Yes, number of unique element will be the longest one. Because we do not want duplicate element, we can always take all the elements. Yeah, implementation, I am here. Probably can someone share an array of length 10 which contains element from 1 to 4? Like, I will show you how does this works. Let's first also forget multiply by minus 1 part. Let's say we will not, we have to find the minimum sequence we have. Let's say this is the sequence I want. Forget -1, let's find the lexicographical minimum. We know that all the elements from 1, 2, 3, 4 appear here. So our final set S contains all the numbers 1, 2, 3 and 4 in some order. So like what I will do is I will find the last index of all the elements. Last index of 2 is this. Last index of 3 is this. Last index of 1 is this. Last index of 4 is this. So what I will do is I will greedily try to find, can I take 1 as the first element? It would be this sequence here. And I can definitely take 1 from here, because even after taking this one, I would be able to get 2, 3 and 4 from here. So I pick this one from here for S. Now my focus is on this remaining sequence. I can ignore 1. I have to take 2, 3 and 4 from here. My first goal would be to take 2 here. And you can see like 2, 3 and 4 last index is this. So I can also take 2 from here, because even if I take this 2, I would be able to even take 3 and 4 after this as well. So the next element I should take probably would be 2. Right now I am trying to find lexicographical minimum, and I am saying like we will not multiply by -1. And what is the minimum answer you can get? That is what I am trying to do. So once we are done with this 2, now we are left with this part. And the thing is, if we take 3 here, we won't be able to take 4 after it. So we are forced to take 4 here, and then we would be able to take 3 here. So my claim is like this is the lexicographical minimum sequence you can get if you don't multiply by -1 before finding the comparison. And the way I have done is, I greedily try to choose smallest element, ensuring that I can take all elements. And probably the way I will summarize it, let's say this is the array we are looking in starting, and we know the set of all the distinct elements. So we can also find a right index such that this part contains all the different elements. So my idea would be, find the smallest element in this part, add it to your answer. Let's say the smallest element appeared here. Now delete smallest element from the complete array, and like you will have some new array which will look like this. Let's say the smallest was here. Or probably I can in fact run some example here. Let me create some array here. Let's say this is my array. So you see like this suffix contains all the elements from 1 to 5. So I will find minimum element in this range up to this. And minimum here is 1. I write 1 in my answer, I delete all the ones here. This is the only place. Now this remaining part contains all the remaining elements here. And I have taken this element, so I cannot take these elements now. Over here, like the minimum element that remains, like I cannot take any element before it, I cannot take any element after it, so I must take 4 here. So I will also delete all the 4s from here. And probably like this is what will remain over here, 3, 2, 5. In this order, I would be able to get it. Probably any questions what I am trying to do? Like what I am saying is, if we are not multiplying by -1 trying to figure out, because I know the final sequence of element, I will try to take some elements in starting. So I will find the largest element in the ending such that the end contains all the elements which I want. And any element which I have taken before it, I will try to find minimum element in that range. I will pick that range and I will move my next pointer there. Probably if there is some good sample, I can probably try to show you around. Any samples which I should probably run over here to show you what's happening there? And to find minimum in a range, we can use range minimum segment tree, which also stores an index. And in case there are multiple elements, choose the one which has the smallest index. The only difference which comes with -1 is for selecting odd index, choose maximum element instead of minimum. And for even index, choose minimum index. Let me try to take one more example. 3, 2, 1, 3, 2, 1, 3, 2, 1. Like this essentially does not help. Like this array contains all the elements from 3 to 1. So because I want to select first element where I will multiply by -1, I should find the maximum element in that range and multiply it by a -1 sign here. And maximum element which is nearest to the index would be 3. So the first element I will choose for S would be 3. Now this 3 is gone, this 3 is gone, this 3 is gone. And again this array contains all the elements from 2 to 1. And because I am selecting odd index, I should select the main index. So in this range, what is the minimum element we can have? Which is this one here. So the next answer would be 3, 1. Once we have selected this, we can no longer select this 2, and also 1 is gone. And now only 2 remains over here. We would select 2, and like 3, 1, 2 would be our final answer here. So this is the answer I have. So I have a segment tree. When multiply, because it's saying for odd index we want minimum element. So this I have range minimum segment tree with me. First I pre-compute all the indexes for all the elements and what is the last position at which they are, and I also keep all the elements which I can take so far. First part of segment tree contains minimum element when element is taken without multiplying by -1. Second part contains element that must be taken when we multiply -1. Answer denotes what is the last taken. And this position last index yet to be taken would be this. Here this array contains last index of all the elements we have in the array. This contains indexes of all the elements we have in this array. This set contains all the elements which we have not taken in the set yet. What are the last indexes there? This is some range minimum segment tree I have, where for each element probably I can keep it a bit better. Range minimum segment tree takes a pair, gives us minimum of A and B. range minimum segmentary for positive and for negative. Now I maintain the last index so taken so far. As long as I have yet to take some elements. The smallest element in last taken index. So elements yet to be taken. Current index, current taken index. If I have taken odd number of index so far, so I should take the one which has minimum sign here. So for current minimum, last taken plus one, and the range up to which I go, like it's open by one there. This would be the element I take. Or if I have to take maximum element, so this comment is now misleading. Take the minimum element by looking at all the elements as negative, or if I have taken odd index so far, take the minimum element when looking at all the positive elements. This would be my current taken index. Now my last taken would become current taken element. So for the next loop, the element which is at current index, I will add it to my answer. I should remove this from elements yet to be taken. And at all the places this element exists, I should probably delete that as well, so that it does not interfere with the next queries I run. We don't really need a erase for IDX. Okay, IDX erase is required. No, IDX erase is not required. Last taken we should definitely. Last index yet to be taken. Here we should remove the current taken index. No, 1 second. From last yet to be taken, we should remove this element. And yeah, this should be the solution. I should probably also remove this segment. Any questions on problem D before we move on to E1? I don't know how to solve E2, so I will not discuss it. Like there are definitely questions which ask us to find lexicographical minimum or maximum something, and the idea there generally is to choose the greedily choose minimum element you can keep while maintaining all the conditions we have. Any questions before we move on to E1? Okay, I will move to E1. It's a deterministic easy version. Consider perfect binary with size 2 into the power n minus 1 with node numbers from 1 to 2 to the power n minus 1 rooted at 1. For each vertex v, 2 into v is the left child and 2 into v plus 1 is the right child. And each node v has a value av assigned to it. Define the pop operation as follows. Initialize v equal to 1. Repeat the following procedure until v is a leaf. Among the children of v, choose the one with the larger value on it and denote such index as x. If the value on them are equal, you can choose any of them. Assign ax to v and assign x to v. Assign -1 to v when we are done. We say that the pop operation is deterministic if there is a unique way to do such operation. In other words, AV is not equal to A into 2V would hold when choosing between them. A binary tree is called max heap if for every vertex u, both AV is greater than equal to A into 2 times V and AV is greater than 2 times V plus 1. Max heap is deterministic if the pop operation is deterministic to heap when we do it for the first time. The second problem asks for first and second time. Initially, AV is equal to 0 for every vertex V, and your goal is to count the number of different deterministic max heap produced by applying the following operation exactly k times. Choose an integer V, and for every x1 path from A to V, add 1 to x. Two heaps are considered different if there is a node which has different values in the heaps. Since the answer might be large, printed modulo P. P is given to you and P is prime. It's guaranteed that sum of n and sum of k for all test cases does not exist also. A lot of stories here. Let's simplify a few bits here. It first says you are given an integer n. So like let's say n equal to 3. So you have a tree which looks like this. This is node 1, 2, 3, 4, 5, 6, 7. Now you can choose some path from here. Let's say if you choose this node, then you add 1 to both of these nodes. In one operation, these has become 1. These are still 0. Let's say next time you choose this node. and you add 1 to everything on this path. So the updated value here becomes, let's say next time you choose this, probably let me choose a different color. Then adding 1 over here becomes, and let's say these are the 3 operations you did. And like now this, let's say this is the heap we have. Here I think it was 1. So what you will do, like let's say this is the heap you have created by adding some prefixes over here. And now we have to count some valid heaps there. AV greater than A2V and AV greater than A2V plus 1 will obviously hold. Because whenever you are adding a node, something to a node, you also add something to their parents. So the only condition we need is when we start from working from a node, like on the path we take, only the 2 childs we get should always have some different values. So here the current value is 3. If you compare these 2 nodes, this node has a maximum value. So next time you move here, and now you look at among these 2 children, so you don't really care what's happening here. This node has a maximum value. So this is a valid tree. Let's say we would have done one more operation here. Let's say we have done one more operation on this part too, adding plus 1 everywhere. Then the nodes here would have become, when we are here choosing maximum worked fine for us, we reach here. But here both of them have same value. So this is an invalid tree. And the problem is asking us, you can do this plus 1 operation k times. You have a node which contains n is up to 500, 2 to the power n minus 1 nodes. You have to find number of possible heaps, different heaps you can get, such that the tree is valid. Any question on the problem statement before we jump on to the solution? Okay, so now my idea is a DP solution. DPMK denotes we have a valid, MT denotes we have a valid heap. Like first thing I will do is if this is my tree, I will try to find a valid heap where when going along maximum, this is the path I take always. The answer is at last I can multiply by the number of leaves to that answer over here, and it's essentially same because you can get equivalent. Like if this is your minimum, you can probably start flipping these 2 trees over here, then these trees over here, and you can probably go on. Finding maximum such that this path makes life a bit easy. So a DP empty says I have 2 to the power m minus 1 nodes. I have done +1 operation t times, and the heap is valid. And the idea is I will try to populate this TP again and again. Let's say this is a heap of 2 to the power m minus 1 nodes. This is another child of 2 to the power m minus 1 nodes. And this is their parent. Now I want to find for this answer dp m plus 1, and let's say I did t1 operation on this tree, t2 operation on this tree. So overall number of operations which are coming from here and value here would be t1 plus t2. And what I will do is dp m plus 1. The tree height is now m plus 1. Total number of operations done is t1 plus t2 plus equal to dp m t1. And because I want to go to the right side, I have to ensure that t1 is greater than t2 into number of ways to do t2 operation on this tree. And like this is, if I keep running for loops like this, I would have my final answer. And like not just t1, t2, there can be some x operations which comes until this node only. There can be some node x which ends, some t3 nodes which ends here only. So we should probably look at that t3 as well. So first thing I would be doing is using mt1 and number of ways I can populate t2 node. I will count how many ways I can populate children of a node of height m plus 1, and then another number of times operations I do over here. Let's create a 2D DP. If the tree is of height 0, then like everything should be 0 for all height from 1 to n. Let's also create like number of ways to just populate child by doing no operations on k plus 1. OP left child, OP left child, OP left child, number of operations on left side, number of operations on right side, so number of ways to populate DP child nodes of height h plus equal to like OP right is equal to number of ways to populate height until h minus 1 and number of operations done on the left side plus number of ways to populate 2 to the h minus 1 nodes with these many operations. 1 second, something I missed there. This should also be one. Like for all the nodes of height 1, 2 to the power 1 minus 1, 1, 3 would be there. Number of ways to populate there would be this. Now we also need like number of ways to populate. Like if we know like the sum of height 2 to the power h minus 1, let's say 5 operations are done over here and 10 operations are done over here. So what can be number of ways to do operations by taking this as a left child, this as a right child, and something as a parent? This is what would be populated over here. Now like number of operations we have done on the child plus number of operations on parent would be number of ways to populate a tree of height h with this as the total number of operations. At last answer would be dp of height n minus 1 because I am populating up till n minus 1 only. K nodes like based on basically how we are indexing over here, and these are the number of leaves. And to like if I know number of ways to populate one child with x node and another child with y node, left count again back here, and we can probably run a for loop again here. And like a prefix sum was sufficient to denote like all the extra operations to get something here would be from side. The main intuition here is you see if you are always going to maximum side, then you see like the number of values 1 on k would be the number of operations you do. The value here would be number of operations you do on this subchild and so on. So if this is your path for maximum, then the operations, let's say if we pick this, the total operations done on this subtree should be less than total operations done on this subtree. And that's where it came in like dph t denotes like my current tree has height h, current tree has height h, and I have done t operations here on this subtree. So this value is definitely t, and all the different values can be different there. Because if you do +1 for any of the node here, that must pass from here. So if there is a t2 here, so you need some ways to count. number of ways to do operation T2 here, and we don't care about what type of tree here. If it's max heap or not. So now like the number of operations done on this subtree would be T1 plus T2. This is what my DP child is. Basically number of ways to do some K operation such that all the nodes end in some children of the tree with height h. And then I can have some set of operations which just ends here. So I use this DP child to populate DP H and T again. And I can keep going over here. So this is some subtree. If T1 operations end on this side, and if T2 operations end on this side, and if this is a valid tree, and we want this to be valid tree, we must also have T1 greater than T2. And because we will never go here, we don't really care about what type of tree over here is. We just know that we should do T2 operations on whatever the number of nodes over here is. And once we fix the number of operations on this part, we add how many operations we should do on this node here. To get number of valid trees on a height, if this was height h, including this node, we will have a tree of height h plus 1. If we keep going it, if we have height n or n minus 1, whatever be the case, then we would be able to find the final answers over here. And since we don't really care about number of operations on this part, we can use the similar idea here. Here we do T1 operation, here we do T2 operation. It doesn't really care whether they are valid or not. We can just use the same thing to find T1 plus T2 operations over there and some number of operations on this node. And like this was the main intuition we had over here. Like because once you are going down, the tree which you are ignoring, you don't really care whether that is a max heap or not. And like that is the intuition. So like when we want to have one valid tree, we can add some random tree over on this side, and we add something there to create a new tree of height, just one more there. Then this is a valid tree, something random would be there. We will add one more tree to get height plus one more over here, and that's what we are doing. So any questions on this one? Like problem statement asks us to do a lot of things, but a lot of things get simplified. This must be equal to sign here. Not sure where it's failing a bit, but yeah. Okay, this must be H1. So I think I will submit this code, and any questions from the chat related to this contest or something else. Looks like I'm missing some edge cases here. This looks fine. Some probably edge cases there. You can probably look at this code where I have modified few bit things and okay, this must be edge. So this pretty much completes my solution discussion idea for all the problems I wanted to discuss today. भैया सीपी अभी स्टार्ट करूंगा तो कितना टाइम लगेगा एक्सपर्ट पहुंचने में so like my answer is always like different people may have different starting background and that may impact like how fast they learn few stuff so. And like it's a bad idea to evaluate something based on a time like by this time I want to be something else. The focus should be more on learning stuff and the rating would come as a byproduct. If a problem is way beyond my range, consider due to E or F, should I directly see the solution and try it? Like directly seeing solution in one go is a bad idea to me. You should definitely spend some time on it and then try to take hint one after the other trying to solve it. Because just looking at solution, you are not learning anything and CP is more about how you can think about different ideas. Like rarely exact problems repeat over there. So there is no point in learning the harder problem solution. There is a very less chance you will find them again. So, any more questions for people in the chat before I call it a day? So, thanks everyone for joining today. Should always begin taking own cases. Yeah, sometimes it's a good idea. Generally, the way I solve it at this point is like I find it difficult to prove some stuff, but I feel I am good at finding counter test cases. So if I don't find a counter test case for some approach, I go ahead and do it. And probably I would say it comes with practice. So probably when you are starting out, you should try proving stuff. And if you are not able to prove it, you should always try to find counter test cases on why something should work or not. And like that is how it becomes like it's a good idea. Begin test cases. Sometimes the penalty for wrong submission is just 50 points. So you can probably see like whether it's worth spending 50 points there or probably just submit once. If it fails, then try to find counter test case there. So thanks everyone for joining today. I will probably end the stream now. Bye.